Hi there. For this assignment, we are gonna do a naive-based classifier and how we can combine it with the logistic regression. It's worth mentioning that we are applying for this case a deep learning model, which we are gonna train the variables specifically for a multivariate probabilistic distribution, which the variable that we're gonna be training in their case, it's the standard deviation from it. For this case, we will be working on the iris dataset, which is this dataset that collects information about the flowers. And we need to predict which type of flower is it. So is it setosa, versicola, or virginica. We can see that the features here will be sepal length and the sepal width. Here we see the distribution of them, or the scatter plot of it. Basically, we will start first the video and the documentation by applying the naive classifiers. What naive classifier is a probability given a dataset to become that label. So for it, you just need to get first a probability that it's called likelihood, or you can also call it class conditional, which means that given a specific label, you want to get the probability of the data set to be that. You also want to calculate the prior probability, which is just the probability of a class to happen. And finally, the event probability, which will be the denominator. In this case, the event's probability, it's a sum of all the probabilities of X, of appearing X in all the different classes. So basically, it's just the probability of X to appear. You finally will get the maximum probability between the three different probabilities in this case that will be applied for each of the different layers that will go. This will become your G hat. So for start, we're gonna get just the prior probability. In this case, will be a classification distribution probability because you are getting three different labels and you want to get the probabilities of each of them to be positive. So you're just getting the division of the amount of times that it appears one of these different labels. You're getting the unique labels. You're getting an array where you will store all of these probabilities, and at the end you will get just the amount of time that it repeats with respect to the total length behind it. Then you're gonna get just an classifier object, which in this case is a distribution categorical distribution. Once you get that, we can get the prior probabilities given the J-trained information and the J labels. And we can see that the distribution, it goes higher for the Iris virginica than the other two. But three of them are really similar and are around the 30% of chance to appearing. So it's really balanced. Next, we can get the class conditional densities, which in this case will be applying a univariate Gaussian distribution. Well, the univariate Gaussian distribution, what it is just that you have a specific mean and a specific sigmoid or a specific standard deviation, and you will be applying the fraction of 1 divided the root square of 2 multiplied by p plus the standard deviation plus the exponential of -1.5 of the difference between the x with respect to the means divided by the standard deviation and that to the squared. But the thing here is that we're going to get it to a multivariate distribution because in this case we're applying it with two different features, the length of the sepal and the width of the sepal. So we are going to get just 12 different parameters, 6 for the mean squares and 6 for the deviation standard. In this case, we're getting one different mean square mean with respect to the label and the feature that it's getting it in that moment. As well as for the standard deviation, it's one for the label with respect to the feature. With that set on, we're gonna get the class conditionals. The function will start first by creating these two parameters that we have already mentioned. We are getting a loop over the different labels, and we're getting both functions, the mean and the variation, with respect to the x is 0, which means that it is getting it is calculating it by column, which means that you're getting the mean per the first column and for the first features, and then you're getting it for the first variables. Sorry, for the variance. And these variants, you will just need to get the square roots in order that it become the standard deviation. With that, you can create the distribution object, which in this case will be a multivariate diagonal, where you are putting the first for the log, which is the parameter which will receive the mu's or the means, and the scale diagonal, which is also known as the covariance matrix. You're getting the sigmoid argument. With this, you will get the conditionals, the class conditionals probabilities, and you can, well, the class conditional distributions, and we can see how it performs over the scatter plot that we have already created. Here we can see that it has a different variation for each of the classes and how it is distributed with the distribution objects that we have already created before. We can see that most of them are like centered to the data set. After this, we can get the prediction of the models. The prediction of the model, what basically is that now we're getting the naive probabilities, and we're getting the g-hats with that. For this, we are getting first, we need to expand the dimensions of the x training variable, and we will get the log probabilities of it in order to get the class conditional probabilities from the distribution that we have already created. It is better to get the log probabilities instead of the normal probabilities, because in this case, we can easier compute the operations. So instead of being a multiplication, it will be just an addition. And same case for the division, it will be just a rest or a minus. You're getting just the difference. And this way, we can also avoid the floating. We can avoid underfloatings, which is just that we're getting the underflows. What it means is that you're getting just a very low data, which the computer can store or can't store. and it will affect this way because if we will be getting the probability between 0 and 1, and we get probability very 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 slow that it just went into 0 instead of 0.00001, then it will affect, when you're trying to get the comparison between the probabilities. So that way we're gonna work with logarithmic. Then we get the log probabilities, which is just to convert from the prior distribution that we have already created the probabilities into logarithms. Then we add them, which means that we are multiplying the probabilities, and this way we will get the numerator of the fraction of naive base. With this, well, it's worth mentioning that we don't have to get the normalization, or in other words, the numerator, in order to just find which is the highest label, because you're just dividing it by the n-scalar. So at the end of the day, at the end of the time, or well, if you have an array where you just have the highest values, and you're just gonna search for the index of the highest, which has the highest maximum, you just need to apply it to that array already. But you want to get the probability behind it, so you want to just get that normalization of the numerator that you have already created. So you're just gonna divide it by the total of the events, and this way you're just creating first this normalization factor, or also calling it the the denominator of the fraction, which is just to apply to the likelihood that you have already created. You are applying this formula over here, which will mean just computing the sum of all the likelihoods multiplied by the prior, which is by you summing all of the probabilities of given x getting into all the labels. It will be just the same as getting the probability of x up to appear. So you just get this way the probabilities of the event to happen, and then you're just converting it to logarithm. Finally, you're just computing you could say the fraction, but in this case, it's just a division because you're working with logarithms. And this way, finally, you're getting the prediction behind it. Well, first, you're getting the argument max you're getting the index of the maximum probability, and you're computing all the predictions. With this set on, we can store the predictions in here and evaluate it with an accuracy given the G-test and the predictions that we have already get, which ones are correct. Because we tested with the X-test, and we get an accuracy of 0. or of the 80% of correction. We can see that the boundaries of our predictions will seem to be like this. So this will be just all of the probabilities that we're not gonna compute it. And we can see that, well, this can improve a little bit. However, what we are gonna do now is not to work with 3 different labels. Instead, try to work with a binary classifier. So we're gonna get first the iris setosa and iris versicola, and iris setosa will be our first label, while iris versicola and iris virginica will get mixed together. This way, we're just computing it by applying it where to the X training binary, which both of them it's just where the virginica appears. Then we set a value of 1 in order to compute as virginica, as versicola and virginica to be the same, and we can plot it this way. Well, next we can get the prior probability of the labels, which is just applying the same function that we have already created by getting the categorical object distribution, and it will appear to be this way. In this case, of course, the combination of both labels, versicolor and virginica, will have more than setosa. And what we're gonna do this way, and why we're trying to compute that in this order of matter of fact, is to understand how the combination between the naive Bayes and to transform it into a sigmoid function or a logistic regression, you will see that both of them can be combined. So basically what we are seeing here is that instead of trying to get the distribution, the multivariate diagonal distribution, instead of computing it with the correct distribute standard deviations, we're gonna compute it related with the points where we can find it. So we're gonna try to mix both distributions of the data set in order to make it more accurate. This way we're getting the standard deviation, as I said at the beginning, just as as a variable that it can be trained. And for the mean variables, we're gonna just get the same numbers that we're getting it for each of the data sets combined for that specific label. So we're getting six parameters in this case. It will be well, six parameters for the mean squared. So six parameters for the mean, which is just for the class and the labels, and two different standard deviations, which will be just for each of the single classes that we have. Okay, so this way, what we are gonna do is first, once we have, um, we're gonna create a function that it will get the variable object of the standard deviation. We're gonna pass through also the data information, which will compute the features and the labels. Then we're gonna pass also an optimizer that in this case we'll see that it's apply the Adam optimizer, and we are gonna pass the number of epochs to train the object that we're gonna create, the distribution that we're gonna create. This distribution will get the number of we're gonna get it will get the mean square, sorry, the mean according to the standard deviation that will be trained. And it will be the same. It will be Gaussian distribution or multivariate normal diagonal distribution. So let's get into the function, how it works. We're first computing the likelihood probability distribution. So as I mentioned before, we're getting the same structure for the mean for each different variable, or for each different feature. We're getting mean with respect of the labels, and we are appending all of them into an array. And then we are just casting it in order for this to be working, because the variable that we have already created, these number ones, they are working with float 32. So in order to it to work, both of the parameters that we are putting into the distribution need to be the same. Let me just 1 second. Okay. Um, Once we have the distribution object created, we're gonna train the model. This is by passing or creating two different lists. The first one, we're gonna get the scaled values or the standard deviation values. And the other one, it will compute just the losses, or it will store the losses. We're gonna first expand, as well as we have done before, the X-training data, the features data, in order to compute the probabilities for the specific distribution that we have already created. So this is a form that it requires to have. And we're starting to compute it in a loop for each of the epochs. We are creating also a gradient tape, which will record all of the gradients. This way, with that object named tape, we're gonna start watching the training variables, which is just an object created for recording or getting the information, and this way computing the gradients. You will see. With that, we are going to compute first the logarithm probabilities of that distribution. With that, next, we're going to get the loss function, which in this case, the loss function is applying this formula over here, which is the minus of the means or the average of the predicted probability for the given class. So in other words, is the probability for the true level, and from all of those probabilities we get the minus average. Then we applied the gradient. We start recording the tape, applying gradients and getting the parameters of the losses and the training variables of that distribution. And we apply these gradients to the optimizer with this function over here. Next, we scale the values. We append them and we will squeeze them later, because this way the training variables that has been computed need to be squeezed them in order for the variable to not have redundant information or arrays or higher arrays, because otherwise it's just getting the array in between different lists. Finally, we are passing the parameters that we're going to get. So for the first case, we are computing the variable. Next, we will set the optimizer as Adam and with a learning rate of 0.01. We specify the number of epochs that we want to have. And then we call the function learning standard deviations in order to compute all of the functions. We can see then the class conditional means that it's stored, and the final standard deviation computed, which was the training variable. We can see then how the plot and loss covariance it is working with respect of the number of epochs. Here we are plotting we can see that once it reached the 100 epochs, the loss, it stays the same. However, for the standard deviation, you need to get the 2000 epochs in order for the standard deviation to converge. Finally, we can see how this works when working with the scatter plot. Here we're just plotting the number of, we're plotting how the behavior of the distributions that we have recomputed over the data set that we have. And finally, we can see the borders of our training group. How does this compute? Finally, we can get the link to the logistic regression. This part is just a way to identify that given a probability or the naive probability that we have already get here, we can see that that probability is the same as the sigmoid function for the logistic regression. This is just by applying a multiplication for the likelihood probability, plus the prior probability, divided that by 1. In other words, this over here will seem to be this here. Or let's say that this over here, it is called probability. And probability, yeah, from likelihood. And we will just multiply this divided by the probability L divided by the 1 of probability L. Will this be computed as the function that appears over here? If we change this part over here and we compute it as A from here, we can see then that the sigmoid function is the same as the naive A probability. In this case, we're just getting the logarithm of the fraction inverted, and that will be the power of the exponential. That will be the minus power of the exponential in the function. It's worth mentioning that given the covariance matrix, this A can be also computed as a linear function of the dataset. It's this based on the Gaussian probability function. So A, in this case, it will be equal to the weights transpose multiplied by the training dataset or the feature dataset plus a certain bias. Given that omega is equal to the inverse covariance of the difference between the mean for each of the labels, and that omega 0 or the bias, it's just the minus 1.5 of the multiplication of the mean 0. You can compute also this as the square root, as the square. So you're getting mu 0 squared plus the inverse covariance multiplied by 1.5 of the, again, we can compute this one as mu1 squared plus the covariance inverse. And all this additional close to the logarithm of the probability given for the probability, the prior probability of the first level divided by the probability of the second level. Okay, with all this said, we just need to get first the parameters of the weights and biases. For the weights, we're getting first the covariance matrix, which a covariance matrix is just the scale diagonal of the standard of the distribution that we have computed elevated to the power of 2. And we are getting also the mean 0 and mean 1. Next, once we have computed both of them, we need to get the bias, which is just applying the same function that we have mentioned before, just that in this case, we're getting the probability from the prior distribution object that we have created, and all of that will be getting by the dot multiplication. Once we have run the function with the prior binary distribution and the plus conditional distribution that we have computed before for this binary object, next we can just compute it over the scatter plot that we have created before. We apply first the logistic by computing the dot multiplication of the data sets with respect of the two different features multiplied by the weights and adding the bias. Then we get the sigmoid of these logits, and with that we can just plot the contornos and how it will be seen before. And that is how you can compute two different things.